Welcome to Copilot Podcasts. What if I told you that one of the most famous unsolved math problems might hold the key to unifying physics itself? Today, we're diving into a mind-bending breakthrough that's shaking up both mathematics and physics.
Oh, this is absolutely fascinating stuff. We're talking about Abdon E C Bishop's recent proof of the Riemann hypothesis using contradiction theory.
Right, and what makes this so incredible is how it connects to quantum mechanics and general relativity. Can you break down what Bishop actually did?
So, according to the research, Bishop took a really unique approach. Instead of trying to prove the Riemann hypothesis directly, he used what's called a contradiction-based proof.
And for our listeners who might not be familiar, what exactly is a proof by contradiction?
Well, it's like saying, let's assume something isn't true and show that leads to an impossible result. If we find a contradiction, our original assumption must have been wrong.
That makes sense. So how did Bishop apply this to the Riemann hypothesis?
He divided prime numbers into two classes, Gaussian primes and non-Gaussian primes. The Gaussian primes map to what's called the ley line.
The ley line?
Yes, it's the critical line where all the zeros of the Riemann zeta function are supposed to lie, at exactly 1/2 on the real axis.
And this connects to physics. How exactly?
That's where it gets really interesting. You know how quantum mechanics and general relativity don't play well together?
Right, it's been one of the biggest problems in physics for decades.
Well, Bishop's work suggests that the mathematical structure behind prime numbers might actually bridge this gap.
Speaking of prime numbers, didn't Euler say something about them being an eternal mystery?
Yes, Euler said mathematicians would never penetrate the mystery of prime numbers, but here we are using them to potentially unlock the secrets of the universe.
Let's get back to the physics connection. How does Bishop's proof relate to quantum mechanics specifically?
According to recent papers, the Riemann zeta function appears in quantum systems as a partition function, basically describing the statistical properties of quantum states.
Interesting. And general relativity?
That's where it gets even more fascinating. Bishop proposes that black hole event horizons are actually charged membranes whose curvature mimics dark matter.
Wait, what? Black holes are connected to this too?
Yes. The research suggests that the curvature of space-time around black holes might encode quantum information in a way that matches the pattern of prime numbers.
That's mind-bending. But how confident can we be about these connections?
Well, the mathematical foundation is solid. The proof uses well-established techniques in number theory and geometric analysis.
But isn't proof by contradiction sometimes controversial in mathematics?
That's actually a really good point. Some mathematicians prefer constructive proofs that show why something is true rather than why it can't be false.
But in this case?
In this case, the contradiction approach seems to reveal deep connections that might have stayed hidden otherwise.
You mentioned earlier about quantum states. Can you elaborate on that connection?
Sure. The Bose-Connes quantum system shows that the Riemann zeta function appears naturally as a partition function in quantum mechanics.
And that's significant because?
It suggests that the deep structure of prime numbers might be fundamentally connected to how quantum systems behave.
This is starting to sound like the universe is built on mathematics in a very literal way.
Exactly. As one mathematician said, number theory is not pure mathematics, it's the physics of the world of numbers.
Let's talk about the practical implications. What could this mean for physics research?
Well, one exciting possibility is that it could help us understand how information behaves in black holes.
The famous black hole information paradox?
Exactly. Bishop's work suggests that information might be encoded in the curvature of space-time itself, preserved in a way that mirrors prime number patterns.
That's fascinating. But wouldn't this require a complete rethinking of how we view space-time?
Yes, and that's exactly what makes it so exciting. It suggests that space-time might have a discrete, number-theoretic structure at the quantum level.
Almost like the universe is digital rather than analog?
In a way, yes. The research points to a kind of quantum discreteness that emerges from the properties of prime numbers.
And this all came from studying an old math problem?
That's the beauty of mathematics. Sometimes solving one problem opens up unexpected connections to others.
Speaking of connections, how does this relate to current physics experiments?
Well, according to recent papers, it could help explain some puzzling observations from the James Webb Space Telescope.
Really? What kind of observations?
They've found galaxies that existed much earlier than our current theories predict, about 300 million years after the Big Bang.
And Bishop's work helps explain this?
Yes, because it suggests a deeper connection between quantum effects and large-scale structures through prime number patterns.
This is really bridging the micro and macro scales of physics.
Exactly. And it might help explain other mysteries too, like the distribution of dark matter in the universe.
It's amazing how a mathematical proof could have such far-reaching implications.
That's often how big breakthroughs happen, by finding unexpected connections between seemingly unrelated fields.
So what's next for this line of research?
Well, researchers are now working to develop experimental tests of these ideas, particularly in quantum systems.
And in terms of practical applications?
One exciting possibility is in quantum computing, where these mathematical structures might help us design better quantum algorithms.
It's incredible how pure mathematics can lead to such practical outcomes.
As Einstein said, the most incomprehensible thing about the universe is that it is comprehensible.
And it seems like we're getting closer to that comprehension through prime numbers, of all things.
Yes, and who knows what other mysteries these number patterns might help us unlock.
Well, that brings us to the end of today's episode of Copilot Podcasts. Any final thoughts?
Just that sometimes the deepest truths about our universe are hidden in the most abstract mathematics.
And maybe Euler was wrong. We are starting to penetrate the mystery of prime numbers after all.
Not just penetrating it, but using it to understand the very fabric of reality itself.
Thanks for joining us on this journey through the mathematical foundations of our universe. Until next time.